We are continuing to study the integration process in section 15.2, but in this section we're going to encounter integrands that are pretty complicated. We're going to be looking at things such as this, where it's inconvenient to multiply it out in order to integrate term by term. So take some time to read the explanation on the first page, and in this video I'll be working through examples 1 through 6. We're going to do a lot of these examples together so that you can really learn this substitution process. Restart the video when you get ready to work example 1. All right, so let's attempt this new substitution process. So looking at the integrand, it is inconvenient to multiply this binomial 3x squared plus 4 raised to the 7th power out. I don't really want to have to do that. We could, but it would take a long time. Our substitution process will be much more efficient. So we're going to look at the overall structure of that function. We have 6x times a function of x raised to the 7th power. Now, I'm going to choose to let this variable u take the place of that function of x, 3x squared plus 4. So I'm going to think of this as u to the 7th power. Looks a lot cleaner and easier to deal with. However, if I'm going to do that, I need to rewrite the entire integrand in terms of the new variable u. I can't have two variables mixed up together. So I've got some leftovers here. I have 6x and the dx left over. Well, we're going to use the du term to cover that. What that means is I'm going to look at both sides of my substitution statement, let u equal 3x plus 4, 3x squared plus 4, and I'm going to differentiate both sides. When I differentiate u with respect to u, I just get 1, but we're going to express it using this differential notation du. So the derivative of the left side with respect to u, we're going to denote as du. On the right side, I'm going to differentiate with respect to x. We'd end up with 6x. Now, we're also going to use this differential notation dx to indicate I differentiated the right side with respect to x. All we really did there was find the derivative of u with respect to x, right? We're just splitting up this differential term so I have a du on the left and a dx on the right. You're going to do that every single time you make that substitution statement. Now, I'm going to rewrite my entire integrand in terms of u. We've already discovered that 3x squared plus 4 to the 7th can be rewritten as u to the 7th. The leftovers in the integral were 6x dx. So notice the 6x dx can now be replaced with du. So everything has been written in terms of u. And this is a very easy integral to calculate. We simply add 1 to the exponent and divide by that same number and then add c. So we have u to the 8th over 8 plus c. However, our original function was not in terms of u, it was in terms of x. So what I want to do is go back and recognize u represented 3x squared plus 4. And I'm going to replace u with that expression 3x squared plus 4. Raise it to the 8th power, divide by 8 plus c. And this is our antiderivative. Now, we better check this one because, again, that was sort of a complicated process. So let's check by differentiation. I want to differentiate my result with respect to x. So I noticed there the whole thing is divided by 8. That's the same thing as having a coefficient of 1 over 8. So we're going to get the 1 over 8 coefficient to the left, out of the way, and then we'll apply the power rule. But keep in mind, the chain rule will also be involved here. So we bring the power down in front, we keep the base the same, and then we decrease the exponent by 1. But the chain rule says multiply by the derivative of the base. Observe that when we simplify this function, we end up with our original integrand. Even though it's in a different order, we know multiplication is commutative, but it matches all of those original details, and that verifies that our antiderivative is correct. Now, that may have been a lot. Integration by substitution is challenging to learn at first, but the more you practice and the more examples you see, the easier it will become. So let's work example number 2. We're going to use the same process. How do I choose the substitution u? Well, I want to look for the inside of a function. Think about your chain rule. When you differentiate something and apply the chain rule, you have some sort of inner function and you have an outer function. In this case, I can see I've got some sort of function of x plugged into a square root function. So that's what I'm going to use for my u substitution statement. So we'll start out, let u equal x cubed plus 1. And as we did previously, I'm going to differentiate both sides with respect to u on the left and x on the right. I'm always going to get du over here on the left side. And then on the right side, differentiating with respect to x, we get 3x squared dx. Now, let's look at our original integrand. We know that we'll be able to write this part as the square root of u, or u to the 1/2. So once that's covered up by a u, let's check out our leftovers. We have x squared dx as our leftovers. Now, I've got x squared dx right here, but it's got extra information. It has that 3. So what I'm going to do, I want to make the right side of this substitution equation, I want it to look exactly like the leftovers in my original integrand. So I'm going to go ahead and divide both sides by 3. And in fact, let's write it as 1/3 du equals x squared dx. Again, all I did there was divide both sides by 3. But du divided by 3 is the same thing as 1/3 times du. So now I've got my leftovers over here on the right side of the integral. So I'll be able to replace both of those with the expression 1/3 du. Okay, let's give it a try. Let's rewrite our integral completely in terms of u. So starting with that big square root function, we decided that's going to be rewritten as u to the 1/2. The x squared dx leftovers are going to be represented by 1/3 du. Now we have a very simple integral to work with. The goal in substitution really is just to recognize the overall operation that's going on in your integrand and to write it in a simpler form. So the 1/3 du, let's just move the 1/3 in front of the integral, get it out of the way, and then we're going to integrate u to the 1/2. When we integrate u to the 1/2, we add 1 to the exponent. 1/2 plus 2 over 2 is 3/2, and we divide by that same thing, and then we add c. We better clean that up a little bit, make it a little more readable. Got a lot of fractions there. So we have 1/3 divided by 3/2. That's the same thing as 1/3 times reciprocal 2/3, u to the 3/2 plus c. And we can clean that up even further by multiplying those fractions, and we've found the antiderivative. The only problem is the original was written in terms of x. This guy is in terms of u. So I have to go back and revisit my original substitution equation. U is holding the place of x cubed plus 1. So I'm going to take that x cubed plus 1 and plug it in for u right here. So we end up with 2/9 times our x cubed plus 1 function to the 3/2 plus c. And that is the correct antiderivative. Now, immediately I want to check it with differentiation for 2 reasons. Number 1, I want to make sure I got the right answer. And number 2, I want to practice my derivative skills. We know that final exam is right around the corner, and we will be calculating derivatives on that final exam. So when we differentiate, we filter our coefficients through to the derivative. Now we apply our chain rule. Exponent down in front. The base stays the same. Decrease the exponent by 1. And chain rule says now multiply by the derivative of the base. And of course the derivative of that constant c is 0. So when we simplify, the 2's cancel. Notice I have 3 canceling into 9 3 times. But over here we have a 3 in the denominator and a 3 in the numerator there. So all of our constants go away, and we can rewrite this and make it look just like our original integrand. The x squared over here, we could move to the left side, and the x cubed plus 1 to the 1/2 is equivalent to the square root of x cubed plus 1. That was my original integrand, so I know that I got the right answer. All right, hopefully you're getting the hang of this. Let's try it again with example 3. Now think for a second, after those 2 examples, do you know what to choose for u? We can't integrate directly because I have a complicated integrand. So we can't do the term-by-term integration. So I want to choose u to be some sort of embedded function, an inner function. So think about it for a minute. Did you choose x squared plus 6x? If you did, you would be correct. Now, not x squared plus 6x squared, I just want the inside function. So this bottom part will be expressed as u squared in the denominator. Now, let's differentiate both sides. Left side always becomes du. The derivative on the right side is 2x plus 6, and I'm going to go ahead and write the dx there. Remember, the right side needs to look like the leftovers in the integral. Now, the leftovers in the integral in this case are the x plus 3 dx. It's close to what we have, but not identical. So what I need to do is manipulate my du equation to make it look just like the leftovers. Observe, we could factor out a 2 from that binomial. Then we could divide both sides by 2, or multiply both sides by 1/2. Now, my leftovers, x plus 3 dx over here, can be covered up in the integral by 1/2 du. Okay, so let's rewrite our integral completely in terms of u. So on the top, the x plus 3 and the dx, that's going to be covered up by the 1/2 du. And in the bottom there, we have u squared. Okay, it's much simpler than the original, although really it's not in the best form. Let's take this 1/2 out in front of the integral. And let's take the u squared from the denominator to the numerator by making the exponent negative. And we have du. Now we have a very simple integral to calculate. So applying our power rule, we add 1 to the exponent, divide by that same number, and add our arbitrary constant. 1/2 times -1 there is -1/2. And we could write u to the -1 as 1 over u plus c. Or how about we call it -1 over 2u plus c. Okay, so we successfully integrated. However, we need our function in terms of the original variable. So I'm going to go back and replace this u with x squared plus 6x. So we end up with -1 over 2 times x squared plus 6x plus c. And that is our antiderivative. Let's do double check it. Now, if I wanted to check it, I would probably rewrite it in a convenient form where I could apply the power rule. So let's find the derivative with respect to x of -1/2 times x squared plus 6x to the -1 plus c. Okay, so again, I'm just rewriting it like this so it'll be easy to differentiate. You could also do the quotient rule if you wanted to, but this way might be a little bit easier. So we applied some algebra to simplify it. Now let's execute the derivative. So we have -1/2 coefficient times exponent -1 times the base as is. We decrease the exponent by 1 and follow the chain rule to multiply by the derivative of the base. That's supposed to be 2x plus 6. Now we can see our two negatives make a positive. Let's work on this term. We can factor out a 2. And write it as 2 times x plus 3. That feels familiar. We've done that once in this problem already. Now the 2's cancel. And then finally, we can manipulate this where x plus 3 is in the numerator. And because of the negative exponent on this factor, we can move that to the denominator and change the sign of the exponent. That looks exactly like our original integrand, and that's a real confidence builder whenever you can check your integrals by differentiation and see that it works out. Okay? All right, let's move on to example number 4. Same technique, but again, just a little bit more practice. So we have 2x minus 3 over x squared minus 3x. Now in this case, there's not really an embedded function. There's not a function of x raised to a power or anything like this. But do notice the relationship between the denominator and the numerator. Do you see that the numerator is the derivative of the denominator? Okay, so it would be convenient to let u be that denominator. Now let's go ahead and differentiate both sides as we've been doing. Du is 2x minus 3 dx. As we observed, the numerator is the derivative of the denominator that we're going to call u. So let's rewrite this completely in terms of u. So on the top we have du, and on the bottom we have u. Now that's strange notation, but that du is sort of like 1 times du, so I could rewrite it 1 over u du. Now we can recognize the antiderivative of 1 over u, do you remember, is natural log of the absolute value of u and then plus c. Now we can replace u with its original expression in terms of x. That's natural log of the absolute value of x squared minus 3x plus c. Okay? Remember, you cannot differentiate something like this term by term if you've got both a numerator and a denominator. You have to either simplify it algebraically like we did in 15.1 or make a substitution. Let's go ahead and check by differentiation. When we differentiate a natural log function, remember we put the argument of the log in the denominator and the derivative of the argument in the numerator. And of course, the derivative of c is 0. So automatically it matches our original integrand, and we are good to go. Hopefully you'll take the time to check your work, especially if you're working on a test. Let's work a problem that involves an e. Example 5, find the integral of x squared e to the x cubed dx. Notice I've got a product here. I cannot integrate each individual factor. Just doesn't work. Think, if I were to differentiate x squared e to the x cubed, I would need a special rule called the product rule. So to integrate it, I need a special process as well. If you have some sort of function of x for the exponent on an e, choose that as your substitution. Then differentiate both sides. Left side is du, right side is 3x squared dx. Now I can see the x squared dx matches the leftovers here, but I'm going to have to get rid of that 3. So multiply both sides by 1/3. And we can see then we'll replace the x squared dx in the original problem with 1/3 du. So rewriting our integral completely in terms of u, we get e to the u times 1/3 du. At this point, you don't ever want to have x's and u's in the same integral. Everything has to be completely in terms of either x or u. When we evaluate this, again, we can move the 1/3 in front of the integral sign. And we have 1/3. Now, do you remember the antiderivative of e to the u? It's a tough one. It's just like its derivative, right? E to the u. What a great formula. That one's easy to remember. Finally, we need to replace our u with the original variable. U represented x cubed. So in terms of our original variable, we get 1/3 e to the x cubed plus c. That's our antiderivative. Let's check it for good measure. If I were to differentiate that expression in red, I would have coefficient 1/3. Now remember, when we differentiate an e, we make a copy of it just as it appears, and then do what? We multiply by the derivative of the exponent. So when we simplify here, we see that we end up with e to the x cubed times x squared, which is in a different order but equivalent to our original integrand. So our antiderivative is correct. All right, take some time to review these substitution rules, following along in your textbook or your e-text. And when you get ready, we'll work one last example, number 6. All right, example number 6 will be different from some of the other examples that we worked. This one's a little bit tricky, so pay close attention and feel free to slow down the video. Go back and listen again anytime you need to. Now, just looking at this integral, what does your intuition tell you that you should choose for u? Hopefully you recognize I've got a function of x under that radical, so I'm going to let u be 1 minus x. So that part in the integrand, we can write as square root of u or u to the 1/2. Now, let's look at the leftovers. The leftovers are x times dx. Notice that when I differentiate both sides of my substitution equation, I'm going to get negative 1 times dx. So it doesn't have enough information. I need it to say x dx. I could multiply both sides by a negative 1. Negative du is equal to dx, but I still don't have x dx. So this is sort of an insufficient substitution as is, unless we recognize I can go from my original substitution equation, u equals 1 minus x, and I can solve that for x. If I solve this for x, I'm going to add x to both sides, and I'm going to subtract u from both sides. X equals 1 minus u. Okay, so I'm just rearranging this. I'm solving this equation for x, and we see x is equal to 1 minus u. So I'm going to replace this x with 1 minus u, and we can replace our dx with negative du. Okay, so little by little, let's rewrite this in terms of u. Okay, so I'm going to start with rewriting x in terms of u. X in terms of u is 1 minus u. So that first term, that first factor becomes 1 minus u. Then, as we've already discovered, the square root of 1 minus x is equivalent to u to the 1/2. And then the last thing we have to work on here is dx. Dx is equivalent to negative du, and all of that is multiplied. Okay, so hopefully you followed every single detail. Each little part has to be rewritten in terms of u. So let's work on evaluating this integral. The first thing that I want to do is figure out what to do with this negative. I know that represents a negative 1, so an easy way to handle it is to move it in front of the integral just like you would any constant. And we have 1 minus u times u to the 1/2 du. Now notice I still have a product there, but the product is different from the original. In the original, which I've kind of made a mess of over here, in the original I couldn't get around this square root. I can't distribute that x into that square root. This stuff is under the radical and this isn't, so those are incompatible factors. But in the case of my u substitution, notice now I can distribute this u to the 1/2 to each term. I can split up those parentheses, and then I'll be able to integrate term by term. So let's do that. 1 times u to the 1/2 is u to the 1/2. U times u to the 1/2 is u to the 3/2. You know where that came from? We're simply adding the exponents. U to the first times u to the 1/2 is u to the 1 plus 1/2, and 1/2 is 3/2. Now we can integrate term by term. I'm going to change colors to show that I'm actually carrying out that operation integration. We know that drops the integral sign and the du sign. So working on u to the 1/2, we're going to add 1 to the exponent. 1/2 plus 2 over 2 is 3 over 2. And then I'll divide by that same fraction. Same thing for that second term, u to the 3/2. When we integrate, we add 1 to the exponent. 3 over 2 plus 2 over 2 is 5 over 2. And we divide by that same thing. And then we glue a plus c out there on the end. Let's invert those fractions in the denominator. If we divide by 3/2, that's the same thing as negative 2/3 u to the 3/2. And when you get used to that, you can automatically flip that denominator when you integrate. Now be careful on the next one. I'm not only inverting those denominators, I'm also distributing this negative. So let's call it plus 2/5 u to the 5/2 plus c. All right, so you want to relax and say, awesome, I found the antiderivative, but don't forget, we need to do this in terms of x. So our original substitution statement said u is equivalent to 1 minus x. So we're going to rewrite this as negative 2/3 times 1 minus x to the 3/2, 2/5 times 1 minus x to the 5/2 plus c. And it would do us good to be patient and go ahead and check by differentiation. So let's do just that. To differentiate the first term here, we have coefficient negative 2/3. Applying the power rule, we bring our exponent 3/2 down in front. We keep the base, 1 minus x, the same, and we subtract 1 from the exponent. The chain rule also tells us we need to multiply by the derivative of the base. In this case, it is negative 1. Next term, we have chain rule again, coefficient 2/5. Exponent comes down in front, base stays the same, decrease the exponent by 1, and chain rule says multiply by the derivative of the base. So let's simplify. In this case, our 3's cancel and the 2's cancel. Notice also that I have a negative times a negative, so even that negative goes away. And I have 1 minus x to the 1/2. Working on that second term, we get a lot of cancellation here as well. All of those constants cancel, but I still have this negative 1 left behind. So we have negative 1 minus x to the 3/2. Now the purpose of checking it is to make sure that it matches the original integrand. And at this point, it doesn't look like the original integrand. But do notice I can manipulate this algebraically. These two terms have a greatest common factor of 1 minus x to the 1/2. If I take that out, I'm going to end up with 1 minus x. Now, how in the world did I do that? Well, notice when I multiply this by the first term, I end up with 1 minus x to the 1/2. Minus in between, and then distribute here. 1 minus x to the 1/2 times 1 minus x to the first. I'm going to add those exponents. 1/2 plus 2 over 2 gives me 3 over 2. So it is successfully factored. Now I can simplify that bracketed element by distributing that negative. The 1's cancel, and I have 1 minus x to the 1/2 times x. Remembering that 1 minus x to the 1/2 is the same thing as square root of 1 minus x, and if I want to sneak that little factor to the left, now this matches our original integrand, so we know that we found the correct antiderivative. All right, work hard on these. Remember, the more you practice, the easier they will get.